Hello, everyone. Welcome to the next meetup organized jointly by quantum computing groups from Washington, Toronto, and Warsaw. My name is Paweł. I'm CEO of the Quantum AI Foundation and one of the organizers of the Warsaw Quantum Computing Group meetup. And I will be the facilitator, the moderator of this meeting. And today we have pleasure to host a great speaker, Xiwan Niu, a PhD candidate from University of Montpellier. And she will give us a lecture titled Circuit Compilation and Error Mitigation for Near-Term Quantum Computing. So as you can see, this meeting is recorded, and so hopefully the video will be later available on our YouTube channel, but there is also live streaming on YouTube. If you have any questions during the talk, please post your questions on our chat, and at the end there will be a Q&A session, so we'll have opportunity to read your questions, to ask the questions, and hopefully Xiwan will answer your questions. Before we start, we'd also like to announce some of our next meetups. So the next one is planned to be in December. Johan Vos, co-founder of Gluon, will give a talk about quantum computing for Java developers, and Shadab will be the moderator. And later, Anna Naden will give a talk about error mitigation and error correction in quantum computing. And we'd also like to thank our partners, our sponsors, support this meetup and help us in organizing and advertising our events. And that's all from my side. So I hope you will enjoy the lecture. And Xiwan, if you're ready, I think we can start, and the Zoom is yours.
Okay, thank you. Thanks, Paul, for this kind introduction. And let me share my screen. Just give me a minute.
Okay.
I think I have some problems.
Could you please try now? Because for some reason, screen sharing was disabled again. I don't know why it happened, but now everything should be fine.
Okay. And I cannot share my screen, but I don't know why. Give me some minute.
Okay, could you please try now once again?
Yes.
All right. Okay, I can see your slides.
Okay, great. So wait me for a moment. Can you see my screen?
Yes, I can see it.
Okay, great. Okay, before I start, I would like to thank Helen for inviting me to this event. I'm very glad to talk about the works that I have done during my PhD on circuit compilation and error mitigation for near-term quantum computing. Here is a summary of my talk, and first I will give a high-level introduction of my thesis topic, and then I will talk about some of the works that I have done, including the qubit mapping problem, parallel circuit execution, and dynamical decoupling for error mitigation. Finally, I will conclude my talk. Quantum computing has made huge progress in recent years. Many quantum platforms based on different technologies have been proposed, such as superconducting qubits, trapped ions, photonic chips, semiconductor spin qubits, etc. Each technology has its pros and cons. The two leading technologies are superconducting and trapped ion devices. Can you see my cursor?
Shuan, there was a question because we still see only the first slide.
Yes.
I'm not sure if that's
oh, wait me for a moment.
That was the intention. Mm-hmm.
This one.
Okay.
It's better.
Yes, yeah.
Okay. And can you see my cursor?
No, at least I cannot see it.
Okay, it's fine here.
So now I can see the first slide again. So
okay. And no
now
cursor, right?
No.
Okay.
Now I can see the summary. Mm-hmm. Good.
Okay, summary and this one and this one, yeah. Here is an example of the architecture of a superconducting quantum computer. We can see it is composed of different layers, and each layer corresponds to a specific requirement of the temperature. The quantum chip is right at the bottom inside of this yellow box, and there are several quantum stack challenges. First, your qubit control must achieve sufficient fidelity so that you can have reliable quantum operations. Second, you need to isolate your quantum system from the environment so that your qubit can have a long enough coherence time. Third, if you want to build a very large quantum computer, the scalability of the qubit is a big challenge. And fourth, you need to realize precise cryogenic technology. To realize such kind of quantum computer requires the efforts from the quantum developer, quantum information scientist, physicist, and hardware engineer. And here is my position. I want to develop some quantum circuits with high quality to adapt the quantum applications to the quantum hardware. Here I list some historic quantum algorithms, and for some reason, the numbers in the complexity are missing. But here the point is to compare the complexity of these quantum algorithms with the corresponding classical algorithms. And for Shor's algorithm, as we all know, it can achieve an exponential speed up. That's the reason why quantum computing is so promising. Various quantum applications have been proposed, such as factorization and some optimization and chemistry problems. But all of these applications require a large number of qubits. And here is the current status of our quantum hardware. It has at most around 100 qubits. There is a huge gap between the quantum hardware and the quantum applications. But the good news is that the error rate of the current quantum hardware is around 0.1%, which is at the error correction threshold. So we can use error correction to close the gap between the hardware and the application. But the problem is that to realize quantum error correction, we need to do the encoding and decoding process, which requires a large amount of resources and is beyond the capability of the near-term quantum hardware. So we need to seek some alternative methods. On the hardware level, people are trying to improve the control technology to reduce the hardware noise, but the control cannot be perfect. And at the application level, people are trying to develop some resource-friendly algorithms to lower down the requirements of the number of qubits and the error rates. But we can see the gap is still not closed yet. The focus of the talk and also the focus of my thesis is to help the quantum community to go one step further to close this step by developing some error mitigation and circuit compilation techniques. Here I list some research topics that I've worked during my PhD, and each topic corresponds to one question that I would like to address. I will talk about each topic in the following slides. The first part is the qubit mapping problem. Today's quantum computers with around 100 qubits are qualified as noisy intermediate skilled quantum hardware. This type of quantum hardware has several constraints. The first one is the nearest neighbor connectivity, which exists in, for example, superconducting and span qubit device. The second constraint are the noisy quantum operations. This figure shows the error map from one IBM quantum chip. We can see the connectivity can only be realized between neighbor qubits. If we want to apply a 2-qubit gate between Q0 and Q2, we need to either swap Q0 and Q1, or we swap Q1 and Q2 to realize the connection between Q0 and Q2. These blocks represent on the other side, these blocks represent the readout error of each qubit, and the two error bars on the bottom represent the H error rate and C naught error rate. It's important to note that the errors are not equally distributed, which means some qubits have lower error rate, but some others don't. We cannot treat these qubits equally. The quantum circuits are designed without considering any hardware constraints. Before we can execute a circuit on the hardware, we need to somehow modify the circuits to make them executable on the hardware. So here comes the problem. How to execute a circuit on the NISQ hardware with these limitations? This problem can be formulated into the qubit mapping problem. It can map the logical qubits used in the quantum circuits to the physical qubits used in the quantum hardware to adapt the 2-qubit constraint. Note that the logical qubits and physical qubits here is not the same notation as in quantum error correction. And this figure shows an example of the workflow of a quantum compiler. We can see on the top is a quantum circuit, and the quantum hardware is at the bottom. Before we can execute a circuit on the quantum hardware, it needs to go through several layers. The qubit mapping problem contains 2 layers. The first one is to allocate an initial mapping to the quantum circuit. And the second one is the mapping transition process, where we will insert, for example, some swap gates to make all the 2 qubits satisfy the hardware topology. Here is a motivational example of the qubit mapping problem. Let's say we want to execute this circuit on the quantum hardware shown in figure B. For simplicity, we just allocate the initial mapping linearly. For example, Q0 in the circuit corresponds to Q0 in the quantum hardware. Of course, we can allocate some other initial mapping. Let's first take a look at G1, which is applied to Q1 and Q2. We can see on figure B, there is a link between Q1 and Q2, which means G1 can be executed directly. The same for G2, which is applied to Q3 and Q4. However, for G3, it is applied to Q2 and Q3. There is no link between the 2 qubits, so we need to either swap Q1 and Q3, or we swap Q1 and Q2 to realize the connection between Q2 and Q3. At the time when we did research, the state-of-the-art qubit mapping algorithm, they treat the 2 swap gates equally and just pick one in random. But they are actually different in terms of the error rate, which I showed errors in the figure. we can see it's better to choose the swap gate between Q1 and Q2 because of the lower error rate. So in figure C, we can see we insert a swap gate, which is marked in red color. The swap gate will change the current mapping so that the final mapping is updated accordingly. In our paper, we proposed a hardware-aware heuristic qubit mapping algorithm. First, we introduced a hardware-aware mapping transition algorithm. In a quantum circuit, if your 2-qubit gate does not satisfy the hardware topology, you need to insert some swap gates. And in general, there are several swap candidates, and we want to find the best one. So here, for the cost function of evaluating the swap candidates, we consider the distance, error rate, and the execution time between the 2 qubits so that we can find the best swap candidate. The swap gate will change the current mapping and have some impacts on the following gates. Sometimes even the best swap gate can have negative impacts on the following gates. So in this case, we will insert a bridge gate instead. It can also execute the non-connected 2-qubit gates without changing the current mapping. By the selection between swap and bridge gate, we can reduce the number of additional gates. We also introduced a hardware-aware simulated annealing method to allocate the initial mapping. Our paper has published in this peer-reviewed journal. Here are some experimental results. First are the results on IBM 5-qubit device. We can see on these two figures, the horizontal axis shows different benchmarks, and the vertical axis on the left-hand side shows the number of additional gates, and on the right-hand side shows the fidelity of the circuit. We compare our HA algorithm with Sabra and Qiskit. Sabra was the state-of-the-art at that time, and it was not implemented into Qiskit, but now it's in Qiskit. We can see comparing HA with Sabra algorithm, the number of additional gates is reduced by 30%, and the fidelity is improved by 21%. We performed the same experiments on IBM 20-qubit device, and we can see our algorithm can also reduce the number of additional gates and improve the circuit fidelity. So now we know we can use our proposed qubit mapping algorithm to execute a circuit on the NISQ hardware with the hardware limitations. The second part is the multi-programming mechanism, and it is also called parallel circuit execution. As I mentioned before, the NISQ hardware has several limitations. First is have several limitations, such as the limited connectivity and the unavoidable errors. Therefore, only small circuits with shallow depth can be executed on the NISQ hardware to get reliable results. As quantum computing becomes more and more popular, there is a growing demand to access quantum hardware, which leads to a long waiting time for the users to retrieve the results. Here, let's say we execute a 5-qubit circuit on this 65-qubit chip. The hardware utilization is only 8%. Most of the qubits are wasted during the execution. When I submitted the job, there were more than 1,000 jobs pending on the device. I really waited for a long time. So here comes a timely issue. How to use NISQ hardware more efficiently while maintaining the output fidelity. The multi-programming mechanism was introduced to address this issue. Here's an example. If we run a 4-qubit circuit on this 10-qubit chip, the hardware utilization is only 40%. But if we run two circuits on this chip in parallel, the hardware utilization becomes 80%. So the key idea is to execute multiple circuits on a quantum chip simultaneously. The idea seems quite trivial, but here are several challenges to develop a multi-programming compiler. The first challenge is to find reliable partitions for each circuit. Since the number of reliable qubits is limited and they are sparsely distributed, it's difficult to find many reliable partitions. The second challenge is to mitigate crosstalk impact. If we execute multiple circuits in parallel, it can increase the probability of introducing crosstalk. The third challenge is the trade-off between the hardware utilization and the circuit fidelity. Of course, we want to run as many circuits as possible to improve the hardware utilization, but we do not want to decrease the circuit fidelity a lot. So there's a trade-off between the two factors. Before I explain our multi-programming compiler, let me introduce the crosstalk impact. First is the crosstalk impact on CNOT error. And here is the error map of an IBM quantum device. We can see if we execute a CNOT gate between Q4 and Q5 independently, the error rate is only 0.8%. But if we execute two CNOT gates on between Q4 and Q5, and the other one between Q1 and Q3 simultaneously, the error rate of the same CNOT pair between Q4 and Q5 is increased by 3 times due to crosstalk. Second, I want to show the crosstalk impact on multi-programming mechanism. Here, we want to execute two circuits on this quantum chip. The unreliable links and qubits are marked in red color. First, we allocate two partitions to the two circuits P1 and P3. They are not adjacent to each other, so no additional crosstalk exists between P1 and P3. And then we fix the partition P3 and move the other partition close to it so that crosstalk exists between P2 and P3. The figure shows the results. The vertical axis shows the fidelity of the circuit. And here the only P3 means the circuit on P3 when it is executed independently. And P2, and here P2 represents the fidelity of the circuit on P3 when two circuits are executed on P2 and P3 simultaneously. We can see the simultaneous execution can decrease the fidelity by 23% compared with the independent execution. The same for the other drop of fidelity, which is 36%. These two drops of fidelity are caused by crosstalk. This example shows that if we want to develop a multi-program compiler, we really need to take crosstalk into account. In our paper, we proposed a quantum multi-program compiler, QMC, and here is the workflow of the compiler. This is the input layer, which contains a list of small circuits that are supposed to be executed in parallel, and the hardware information, including the hardware topology, calibration data, and crosstalk properties. The crosstalk properties of a quantum device is characterized by the simultaneous randomized benchmarking protocol. The parallelism manager works with the multi-programming compiler to determine the number of simultaneous circuits. And then these circuits are passed to the multi-programming compiler. It will allocate the reliable partitions to these circuits by considering the hardware calibration data, the topology, circuit information, and crosstalk. The circuits are passed to the scheduler to perform the mapping process so that the circuits can be executable on the quantum hardware. And we can finally obtain the results in the output layer, and you can find our paper here on arXiv. Here are some experimental results. First, we execute 2 circuits on IBM 27-qubit chip. And the 2 figures shows the results. Again, the horizontal axis shows the benchmarks, and the vertical axis on the left-hand side shows the fidelity of the circuit, and on the right-hand side shows the number of additional gates. Here we compare QMC with PHA. QMC means that we run the 2 circuits in parallel using our multi-gram compiler, and PHA means there is no parallelism. We just run the 2 circuits sequentially like a general quantum compiler does. From the results, we can see the simultaneous execution can decrease the fidelity by 5%, but the number of additional gates is almost the same. In this case, the fidelity is decreased by 5%, but the hardware utilization is improved by 2 times, and the total runtime of the circuits is decreased by 2 times. Here are the results when we execute 4 circuits simultaneously on IBM 65-qubit chip. We can see the simultaneous process can also decrease the fidelity a little bit, only 6%, but the hardware utilization again is improved by 4 times, and also the total runtime of the circuits is decreased by 4 times. So there's a trade-off between the hardware utilization and the circuit fidelity. Here is an application of applying the multi-programming mechanism to VQE algorithm. We showcase to estimate the ground state energy of deuteron, which can be modeled using a 2-qubit Hamiltonian spanning these 4 polystrings. If we use the naive measurement method, we need to construct 4 measurement circuits for these polystrings to calculate the expectation value, which introduces a large overhead. Therefore, the poly-operator grouping method was proposed to reduce this overhead by grouping the commuting polyterms and measure them simultaneously. In this case, only 2 measurement circuits are needed to calculate the expectation value. Our idea is to apply the multi-programming mechanism on the top of the poly-operator grouping to further reduce the number of measurement circuits. Here are the results of 4 optimizations, which correspond to 4 ancestor circuits. If we use poly-operator grouping method, we need 8 measurement circuits. So first we run these 8 circuits in parallel, and the results are marked as PG, which means poly-operator grouping. And then we run these 8 measurement circuits simultaneously using our multi-programming compiler. The results are marked as QMC PG. The 2 figures show the result. The horizontal axis shows the 4 different parameters corresponds to the 4 ancestor circuits. And the vertical axis shows the expectation value. We repeated this experiment for 5 times, and we compare the results with baseline, which we just execute the circuit using the simulator. From the results, we can see again the error risk is increased a little bit, but the hardware utilization is improved by 8 times, and the total runtime is decreased by 8 times. This application shows the benefits of applying multi-programming mechanism to VQE algorithm. Here is a summary of the multi-programming algorithms at the time when we did the research. We compare our QMC algorithm with the state-of-the-art, and we show some features which might be considered using in the multi-programming algorithm. We can see only our QMC method and this CNA algorithm consider crosstalk, but in different process. Both of us use the simultaneous randomized benchmarking to characterize crosstalk. For the other two methods, they do not consider crosstalk during the parallel circuit execution. But the limitation is that performing simultaneous randomized benchmarking on a quantum chip requires a large overhead. Here, this table shows the overhead of performing SRB on two different IBM quantum chips. So in this paper shows in the bottom, they propose some optimization methods to reduce the overhead of SRB. We applied these optimization methods, but here we can see we still need more than 100 jobs to perform SRB for crosstalk characterization for these two IBM quantum chips. Imagine if we have a very large quantum chip, the overhead of performing SRB cannot be ignored. Therefore, in our paper, we proposed a quantum crosstalk-aware parallel circuit execution method, which can also reduce the crosstalk impact during parallel circuit execution without SRB overhead. Experimental results have shown that the crosstalk impact is only significant on signal pairs with one hop distance, like shown here in this figure. In our paper, we introduce a crosstalk parameter, which can represent the crosstalk impact on this type of signal pairs with one hop distance. When we allocate a partition, we check the signal pairs inside the partition if they are one hop distance away from the already allocated partition. If this type of signal pairs exist, we collect them as potential crosstalk pairs, and we use our crosstalk parameter to time the signal error rate to indicate crosstalk impact. By doing this, we can somehow reduce the crosstalk impact without the need of using SRB to quantify the crosstalk impact. You can find more details of our method in this paper published in Date Conference. Here's an application of applying the multi-program mechanism to zero noise extrapolation method for error mitigation. ZNE is an error mitigation method which requires two steps. The first one is noise scaling, which means we can scale the noise of the circuit by, for example, extending the circuit depth. And then we use an extrapolation method to extrapolate the noise-free expectation value. The limitation of ZNE is that it needs to execute one circuit multiple times with various depths to realize the noise-free extrapolation. So our idea is that we can execute these circuits with various depths just in parallel so that we can do error mitigation in one circuit execution. Here are the results. In this figure, the horizontal axis shows the benchmarks and the vertical axis shows the absolute error, and lower is better. So here we compare baseline, QCP, and ZNE. Baseline means we just run this circuit independently without using any error mitigation method. QCE plus ZNE means we run these circuits with different depths in parallel. And ZNE means that we run these circuits sequentially, just like the general ZNE method does. we can see even though the multi-programming method, the results of the multi-programming method is not as good as the general ZNE technique, but it can reduce the error rate by 2 times compared with the baseline. Since we construct 4 circuits with different depths, we can improve the hardware utilization by 4 times and reduce the runtime by 4 times. Here is another application of applying multi-programming mechanism. So now we know we can use the multi-programming mechanism to use NISQ hardware more efficiently without losing much circuit fidelity. The third topic is dynamical decoupling for error mitigation. First, let me introduce dynamical decoupling. The idea is to suppress the decoherence error by reducing the interaction between the quantum system and the environment. So here the system goes through an idle time. We can see during the idle time there is no quantum operation, but there exists the interaction between the system and the environment, so that the qubit might lose its state information. Instead of letting the quantum system going through an idle time, we can insert the dynamical decoupling sequences during the idle time. And in this table, we show different DD sequences such as Hanako, CPMG, XY4, UDD, KDD, etc. The DD sequences can be realized by some quantum gates, and the overall performance of the DD sequence acts like an identity gate, so that the qubit state before and after the insertion of DD sequence keeps the same. Here, for example, we insert 2 X gates during the idle time. It can reduce the interaction U1 and U2 with the environment. At the bottom, we show an example of inserting DD sequence to a quantum circuit. First, we use the as late as possible scheduler to schedule this circuit. We can see there's some delay here, which is equal to the duration of the CNOT gates. And then we insert the X2 DD sequence. Here we can see the 2 X gates. This example shows basically how we can insert DD sequences to a quantum circuit. Given these different DD sequences, we want to see what are the impacts of these DD sequences on the quantum algorithms and quantum hardware. So first, we insert these 9 different DD sequences to Bresston-Vazirani algorithm. Here are the experimental results. In the figure, the horizontal axis shows the BV circuit with different qubit number, and the vertical axis shows the relative circuit fidelity. If the relative result is larger than the baseline here, which is set to 1, it means DD can improve the circuit fidelity. Otherwise, it means DD will decrease the circuit fidelity. We performed the experiments on 4 different IBM quantum chips with different qubit number and quantum volumes. We show the maximum, minimum, and average results of the 9 DD sequences and the different PV circuits. We can see all the DD sequences can improve the PV circuit fidelity to some extent. And in general, UDDX performs the best. Then we want to insert these DD sequences to hidden shift algorithm. First, we check the circuit of HS algorithm. We can see the idle time is always introduced by a single qubit gate, which is too short to fit any DD sequences. So it means we cannot insert DD sequences to each S algorithm. And here are the experimental results on QFT circuit. We can see in this case, DD can also be beneficial for QFT circuits, but the improvement is not as large as for PV circuits. And DD sequence is more favorable when the number of qubits is more than 5. Here are the experimental results on graph state circuit. We can see for this type of circuit, the performance of DD is not very encouraging and is different across IBM devices. It is only beneficial for IBM Guadalupe device, but not for the other 3 devices. So now we know the effects of applying DD sequences to some quantum algorithms. And then we want to learn to focus on another optimization method called pulse-efficient transpilation method. For IBM quantum hardware, it only has 1 2-qubit operation in the basis gate size, which is the CNOT gate. It means that if we want to execute a circuit on IBM quantum hardware, all the quantum operations must be decomposed into CNOT gate and some single qubit gate, which might not be very flexible all the time. At the hardware level, the CNOT gate is implemented by a RZX gate with pi/2 rotation and some 1 qubit gates. If we use the pulse-efficient technique, we want to decompose the circuit into the RZX gate into RZX basis with an arbitrary rotation. So here is an example of decomposing the RZZ gate. First, we decompose it into the CX basis. We can see we obtain 2 CNOT gates with 1 RZ gate. The duration is more than 2000 DT. Then we decompose the same circuit into the RZX basis. The duration is only around 1000 DT. There's more than 50% of reduction for the duration of the circuit. Now we want to ask, will the combination of dynamical decoupling and this pulse-efficient optimization method further improve the circuit fidelity? We evaluate the 2 techniques on QAOA circuits for solving the max cut problem. And here are the experimental results. Figure A shows the results when only DD is applied, and figure D shows the results when both of the 2 techniques are applied. Note that the range of the vertical axis is not the same for the 2 figures. For the figure B is 0.15, and for figure A is 0.10. So it means there's an improvement on figure B. Here are the complete results of the 4 quantum hardware. The first line shows the results when only DD is applied, and the second line shows when only PE is applied. And the last line shows the results when both of the 2 techniques are applied. We can see only applying DD or PE can already increase the circuit fidelity for QAOA algorithm, and the combination between the 2 techniques can further be beneficial for the circuit fidelity. In general, CP-DD sequence performs the best and KDD performs the worst. Here are some guidelines. First, the performance of DD is highly application dependent. It has shown good results on PV and QAOA algorithm, but not on the other algorithms that tested. Second, it is recommended to check the structure of the circuit to verify if DD is able to be inserted. Third, the robust DD sequence key DD does not work well on IBM devices for most of the quantum algorithms tested. QDD is a DD sequence which is supposed to be resilient to pulse imperfections. It has shown the best results on Rigetti device, but not on IBM quantum devices. And fourth, the pulse efficient technique is favorable for QAOA circuits, and combining it with DD can further advance the circuit fidelity. So now we know the effects of applying dynamical decoupling for error mitigation. So to conclude, the main contributions during my thesis can be divided into two parts. For error mitigation, for circuit compilation, first we developed a qubit mapping algorithm to execute a circuit on a NISQ hardware with the limitations. Second, we developed a multi-programming compiler to improve the NISQ hardware utilization without losing much circuit fidelity. For error mitigation, we tried to reduce crosstalk impact for the multi-program mechanism, and we also explored the effects of dynamical decoupling for decoherence error mitigation. If you are interested in the details of our works, you can check our papers here, and all the code of my papers are posted in GitHub. And finally, I would like to thank my funding agencies, the Quantum Initiative of the Region Occitanie, University of Montpellier, and IBM Montpellier. Thanks for your attention, and I'm happy to answer your questions.
Okay, great. Thank you very much, Siwan, for a great presentation. And yes, we have some questions on our chat. So the first question from Kevin. I think it was related to one of these slides close to the beginning. It appears that many measures have been taken in circuit design to accommodate for hardware limitations. Could you comment on how these developments will be beneficial when error rates are reduced?
Sorry, you mean the measurement?
So maybe I will read it once again.
Yeah.
It appears that many measures have been taken in circuit design to accommodate for hardware limitations. Could you comment on how these developments will be beneficial when error rates are reduced? Or Kevin, if you are still with us, I can see that you are with us. Maybe you can also unmute yourself and maybe clarify as well. I think it was closer to the beginning.
Yeah, it's, the beginning with all this is basically, the swaps and stuff like this. It seems like in everything quantum computing is just dealing with noisy hardware, especially in the past couple of years. How will this work that's been done be beneficial in the future when error rates reduce?
I think if in the future, if we have a very large quantum hardware which can realize the quantum error correction, the compilation technique will be completely different from this kind of compilation technique in the NISQ era. Here, this technique, in my opinion, is focused on the NISQ hardware. And since NISQ hardware has unavoidable errors, if we can somehow reduce the errors during the circuit compilation, the results can be more reliable.
Okay, and then kind of going off that with the IBM news is they say they're going to use error suppression and mitigation without doing error correction. Do you believe that that will be an effective approach for next year?
Yes, I think because we are still a long way, there is a still big gap between to realize quantum error correction. So now people are trying to focus on error mitigation to see if we can find some real quantum applications on the NISQ hardware.
Okay, awesome. Thank you.
You're welcome.
Great. Thank you, Kevin. Thanks for asking. There's another question from Virenda. NISQ devices mean we refer to 50 qubits or more. So which areas we can use the NISQ hardware for actual useful applications to surpass classical computers, or is it still very limited to research arena only?
I think for NISQ hardware, we haven't found any real applications that can outperform the classical computers, but there are some promising areas such as quantum chemistry, like people are developing VQE algorithm to maybe find some applications in the chemistry and also in optimization problems, like people are target the QAOA algorithm. And also I also know some people, they work on quantum machine learning but still we didn't find any real quantum applications yet.
Mhm.
So anywhere, so you think that NISQ hardware could be leveraged because recently the pandemic pushed us to get into the evaluation and release of vaccination and medicine very quick so that we could control the pandemic. Any such application do you think will also be a good candidate to find usage through this hardware?
In my opinion,
Chemistry, I'm extrapolating beyond chemistry to pharmaceuticals. That's why I extended the question.
yes, but in my opinion, there's still a long way to go. So
it's still in research.
Yeah. Yeah.
Thank you.
Mhm.
Good, thanks. I can see that Ron has raised his hand, so Ron, you can unmute yourself and ask question.
Yeah, hi. If I understood you, you're using compilers to remap the qubits and do some other operations to attempt to mitigate error. Is this done in the compiler as a separate pass or a separate module? Is it something that would be interchangeable in the future? And also, if it is done in multiple passes and layers, is there an established set of parameters so that these layers can talk to each other, like in the form of an API or something like that?
Yes, during the compilation here, I only introduced the mapping process, which is only one layer in the compiler. There are many different compilation passes. I don't know if it answers your question.
Right. So those layers, the mapping transition and the initial mapping, those are layers that would be interchangeable as new research is found as to how to do remapping or how to do better noise mitigation.
Yes, and yes.
And so my other question though is, is there an internal standard for how these layers communicate with each other?
I think it's an ongoing research topic because you can, of course, you can reorder these different steps and the performance will be different, but we do not know the optimal way to order these steps.
Okay. All right. Thank you.
You're welcome.
Right, great. Thank you, Ron. Okay, do we have more questions from our participants?
Yes, we have.
Yes.
I have question and comments.
Mhm.
First of all, you mentioned simultaneous measurements, 8 of them. And I wonder about the collapse due to measurements and other difficulties in the fact that measurement happened. The other comment, while you consider the answer, is that for those of us who are not that familiar with hardware, like I've learned a lot from your talk because I'm not familiar. Also, I learned that IBM is doing experiments in different locations in the world. So I should go on their website and find out more description. And the other comment would be, you are writing a thesis, or you finished actually your thesis by the number of papers that you quote. So this is not thesis defense. This is talking to public. Some are experts and some are learning. So for the future and also to the organizers, it's possible to make some tutorial by the presenter so people who plan to attend and learn can familiarize themselves with some basics, because you did talk a lot of information, but very, very fast. So still congratulations for fantastic knowledge, and yet there are some improvements in the future.
Okay, good. Thanks for your comment, Itamar.
What about the measurements?
Could you please repeat the question?
Yeah, you mentioned 8 measurements that happen simultaneously.
Mhm.
To my knowledge, even one measurement has some problems that wave function may collapse, and we will lose that information or part of the information. Now, when 8 measurements happen, does it mean that you did 8 measurements simultaneously?
Yes, the 8 measurement circuits, the 8 measurements means the 8 measurement circuits. We run the 8 circuits in parallel. So when we design the multi-prime compiler, we already take because the collapse of the measurement is due to the errors. And when we develop the multi-programming compiler, we already take the measurement error, the synod error of the qubit. So we want to mitigate these errors. But still, we can see comparing with the simultaneous execution with the independent one, the error risk is increased due to the simultaneous measurements.
So I'll show my ignorance. Is this 8 measurements are doing like backup from one another in case one is failing, like in the sense of fault tolerance?
No, it's
No.
just to showcase the performance of multi-programming mechanism.
Okay, so that's like a concept of parallel computing.
Yeah, exactly.
Fantastic. Thank you very much.
Okay, thank you.
Okay, there's one more question from Yusuf. He's asking about what is KDD. KDD. I think it was about dynamic decoupling, right? Clear dynamic decoupling, maybe.
Yes, as I mentioned, I think I explained during the talk, the dynamical decoupling or the DD dynamical decoupling sequences are some pulses, but the pulses can be eventually represented by some quantum gates. So you can just understand the DD sequence like a sequence of quantum gates. And here in the pulse implementation in the table, I show the corresponding quantum gates of the DD sequence.
Yes, yes. And what exactly is KDD stand for?
KDD, I think is the name of the person who invented the DD sequence, but I'm not sure. I recommend you to check the paper. Yes.
Okay, I've just checked that it's probably CNIL dynamic decoupling, so probably the name is CNIL. All right, thank you. There was a question from Kevin about recent side-by-side comparison of quantum computing hardware limitations, but it looks that it has been answered by Kenneth, right? So Kenneth just pasted the link, the PDF. So I believe that, Kenneth, I believe that your question is already answered, right? Or maybe, yes, good. And there's another question from Yusuf. Do you run circuit multiple times? So
yes. For each circuit, I think I run it thousands of times, but I cannot remember the exact number.
Okay, great. Thank you. Do we have more questions from our participants? Another question from Yusuf.
I have a question.
Yes, go on, Itamar.
If I read your GitHub code, that means that I can run some of these experiments the so-called in silico, like on computer?
Yes, you can run these experiments, but you need to have the access to IBM quantum hardware.
I cannot do it in Google Colab.
Yes, sure, you can do that. But if you want to execute the circuit on the quantum hardware, you need to have the access.
No, I'm not interested in close touch with hardware. I'm not experimentalist. I'm thinking concepts and maybe software. Even in this, I'm a little bit limping. So that's why I'm asking this naive question. But thank you so much. I will learn the GitHub code if I can. Thank you very much.
Okay, great. Thanks, Edgar. There's another question from Yusuf. How do you calculate the delay?
The delay, you mean in this figure?
So Yusuf, maybe you can clarify what exactly you have in mind here.
Yes, in this figure, is it with the IBM hardware? When we have access to it, you can estimate this delay.
Yes, and in their hardware, they have as late as possible scheduler paths. And if you apply this path, they will calculate the delay automatically.
Okay, so then you can know how many X you can apply for dynamic decoupling.
Yes. But it depends on your setting. If you here for this example, I only insert the DD sequence for one time, which means only 2 X gates are inserted. But of course, you can insert DD sequences for several times. If you insert it for 2 times, 4 X gates will be inserted.
Okay, that makes sense. And is it only used with X gate because X dagger is equal to X, or we can apply it to any gate by inversing it, or
there are different there are different DD sequences, and you can insert X gate, Y gate, something like this. But when you transpile the circuit, the single qubit gate will be decomposed into X gates and some RZ gates.
Okay, thank you. Okay.
Yeah.
Okay, good. I got some more questions on our chat. Maybe someone would like to ask last question.
Yeah, I've got a question. So, despite the limitation of the nearest neighbors, there's obviously many other hardware technologies. Why, in your opinion, do you think that this may be the primary, or if not the only technology that will make it with quantum hardware?
You mean the nearest neighbor or superconducting?
Well, say for instance, like ion trap is slower, but a lot more flexible. It seems like, as far as different qubits and the arrangements and things you can do with it. So my question is have you looked at other quantum technologies, hardware technologies, as far as like I know some companies, they do both. They do gate-based superconducting qubit and ion trap, just depending on the problem.
I haven't thought about this, but I've tried the quantum quantum chip as well. And from my experiments, I think the circuit executed on the quantum have higher fidelity than IBM quantum chip. I think because the errors of quantum machine is better than IBM quantum chip, but the qubit number is very limited. It only has like 20 qubits, if I remember it correctly.
Yeah, they seem next year the area is like 32 qubits, and obviously the 433 this week with IBM. So it's just interesting as far as, because if you type in whatever, they say maybe more practical. It's a huge field. I appreciate the presentation. I got to go. Thanks, everybody. This has been informational. Have a good rest of your weekends.
Great. Thank you, Kevin. Have a good weekend. Okay. Do we have more questions? I don't see more questions on our chat. I don't see any raised hands, so I think we can finish for today. And there was a comment from Ron. There is also
No,
possibility.
I also have a question.
Yes, go on.
Is it possible, is this study is applicable only on IBM hardware or like other hardware like neutral atoms or with other hardware is possible to apply the same study?
I think if they have, for example, the nearest neighbor connectivity, you can, of course, apply this technique. And for dynamical decoupling, I think it's applicable to any technologies. Does this answer your question?
Yes, thank you.
Great. There's, I think, another question from Ron on our chat. There is a lot of possibility for neutral atom qubits. Will this error communication algorithms transfer? I'm not sure if you are able to give the answer, but yes. So I will maybe read it once again. There is a lot of possibility for neutral atom qubits. Will this error meet algorithms transfer?
Actually, I'm not very familiar with the neutral atoms, but I think I've read many papers, they tried at least to use DD for the different technologies to improve the T2 time of the qubit. So I think it's applicable to any quantum technologies. I mean, this dynamical decoupling technology.
All right. Good. Do we have more questions? I don't see more questions on our chat. I don't see any raised hands, so I think we can finish for today. So, Chuan, thank you once again. It was a great presentation. Thanks for answering all the questions. We'd also like to thank our participants, also for many interesting questions. So it looks like it was very informative. And I think we can finish, and we invite you once again to attend our next meetups. Next one will be in December. So thanks once again. Have a good weekend, and good luck in your quantum computing journey.
Thank you.